Assalamu alaikum. I am Tanvir Alam Roni. Today I am here to present my paper Dual Side Polished SPR Biosensor with Wide Sensing Range. Throughout the session, I'll try to present the following topic: abstract, introduction, design and methodology of our sensor, analysis, results, comparison with previous sensors, and finally conclusion. We have designed a biosensor with a wide sensing range that can measure a wide range of biomolecules with RI from 1.21 to 1.4. Our proposed sensor is based on photonic crystal fiber. The sensing mechanism is based on surface plasmon resonance. It can be operated in the optical to near IR region. In next few slides, PCF and SPR will be briefly discussed. Photonic crystal fiber, a class of optical fiber, based on the properties of photonic crystals. First explored in 1996 at University of BUET, UK. Because of its ability to confine light in hollow cores, or with confinement characteristics not possible in conventional optical fiber. PCF is now finding applications in fiber optic communications, fiber lasers, nonlinear devices, high power transmission, highly sensitive gas sensors, and other areas. PCF is a compact and lightweight structure that allows miniaturization of the sensors, which make them more feasible for remote sensing. Now, SPR, an optical phenomenon, is defined as the collective oscillation of free electrons on the interface between the dielectric and metal. When the wavelength of the surface electron matches with when the wavelength of the surface electrons matches with that of the incoming photons, resonance occurs. At the resonant wavelength, maximum loss for a given analyte is obtained. Any tiny little changes in the RI causes the peak shift, and an unknown analyte can be detected by the shift of the loss peak and respective wavelength. Previously, prism-based sensors are used for sensing purpose, but they are costly and bulky. Later on, conventional optical fibers are introduced as sensors. They are lightweight, but in case of designing the sensor, this type of sensor is not flexible. PCF-based sensors solve this problem. Two types of sensing mechanism: internal and external. For real-time sensing, internal sensing is difficult, so we choose the external sensing mechanism. We propose an external sensing based novel dual-side polished gold-coated PCF SPR sensor. It can be operated in the optical to near IR region. We have introduced a circular-shaped core structure which make the coupling easier and that improves overall sensing performance. The outer surface of the fiber is coated with gold with the plasmonic surface in direct contact with the analyte. Here, electrical field distribution of the sensor in core and SPP mode are shown. Throughout the study, we have only worked with Y mode, as the confinement loss in Y mode is way larger than the X mode. At the resonance point, real part of the effective refractive index is same, the core mode and SPP mode. This is the phase matching point. Confinement loss is maximum here. This particular point is very significant for sensing operation. In the next few slides, Analysis of the sensor will be presented. Gold layer thickness has a significant effect on both the amplitude and the wavelength sensitivity. Therefore, it influences the overall performance of the sensor. As shown in the figure, there is a positive horizontal shift and a negative vertical shift with the increase of gold layer thickness. For a particular analyte, a thicker gold layer results in a broader loss peak and an increased SNR of the sensor. So, we have selected the optimum thickness for the gold layer to be 40 nanometer. There is a negative vertical shift with increasing of pitch distance. The resonance wavelength is almost independent of the pitch. We choose the pitch distance as 2 micrometer as the confinement loss is low here. Increasing the value of diameter of the outermost air holes results in a positive vertical shift of the loss curve, and the resonance wavelength remains almost unchanged. We choose this equals 2 micrometer as optimal value as there is a sharp peak at the resonance wavelength. After numerical analysis, we have found optimum values for the following design parameters. With this optimum design, we have calculated the confinement loss. We are able to get the confinement loss curve for analyte with RA from 1.21 to 1.4. From the confinement loss curves, we determine the corresponding amplitude and wavelength sensitivity. In these slides, the amplitude sensitivity curves are presented. We have calculated the following performance metrics with some equations presented in the paper. The sensor has a maximum amplitude sensitivity with 1277.47 per RIU and wavelength sensitivity of 5000 nanometer per RIU. Sensor resolution is 2 into 10 inverse 5. Our sensor can permit a wide range of light source from optical to near IR and can detect a wide range of analyte with RI from 1.21 to 1.4. In the paper, we have compared the performance of our proposed sensor with some recent PCF-based SPR sensor. Our wavelength sensitivity is very low, but if we look at the resolution, this is enough for modern analyzer to detect any analyte. Compared to any prior sensor, our sensor has a wider sensing range. So, using our single sensor, a wide range of analyte can be detected. Finally, our proposed PCF-based SPR sensor having a wide range of detection. Commercially available lasers can be used as light source. Our design structure can easily be fabricated with existing technology. Thank you.